All right, why don't we go ahead and get started. So welcome back, everybody, to EE290C. It's just a couple of administrative things. Obviously, the homework is due this Thursday, so hopefully you guys are well on your way on that one. And then also just, obviously, ISC is next week, so no lectures, because I'm assuming that everybody will be there. And then we'll obviously pick back up the following week. I will probably assign a homework kind of over that period of 2 weeks or whatever it is. So, stay on the lookout on the web for that, but I definitely won't do that before, let's say, like Thursday or probably even beginning of next week or so. So on that note, how many of you guys have actually started the homework already? Okay, so reminder, it is indeed due in 2 days, so if you didn't raise your hand, then now is as good a time as any to start. Any questions before we sort of dive back into material? Yeah?
Yeah, so in the second question, is that a ZFE equalizer or MMSE or...
Oh, so I believe in the second question, I was assuming that people will use a ZFE, but it's kind of up to you. But I was assuming a ZFE, I believe. So,
I haven't given an SNR, so it's just...
Yeah, so I didn't give an SNR, so you probably the only thing that would make sense is to try a ZFE. You can, I guess what an SNR is, but yeah, that's what I'm assuming.
Also, right? The one without the SNR.
Say that again?
There's one without the SNR too, right?
No, so the only place where I basically asked about MMSE, I actually gave you the SNR.
Okay.
Yeah.
And in the first question, can you just set any tab to the cursor value or?
You mean in terms of where like what's your desired channel? You can do anything you want as long as you meet the specifications. I believe I set most of those channels up in a way that it should be sort of fairly obvious what the cursor is, but you can do anything you'd like. Other questions or? Okay, so let's actually dive back into the material. So just as a reminder, since it's been about a week, last time we were sort of talking about just how you really evaluate the performance of high-speed links. And as we started talking about, it's actually sort of a more involved question than you might first think. So what we started out by saying was that there's kind of this traditional approach that people usually, or I should say maybe about 10 years ago or so, was kind of the standard approach that people were taking, which was really borrowed from computer systems. And that was really just based on sort of a worst case analysis. Because there it was really, you wanted Burr less than some ridiculous number, something like 10 to the minus 20. So you just really tried to find what was the absolute worst case thing that could possibly happen, and then guarantee that things would still work in that case. And as we sort of started talking about, the way you would typically do that would be sort of, you do a voltage timing budget, right, or a VT budget. So we talked a bit about sort of the voltage budget. That's already been in your homework, or so hopefully if you've started that, you have an idea of what that kind of looks like now, so I won't review that now. We also talked a little bit about kind of the timing budget, but really the key in both of them was that we said that what you really have to do is separate out the random sources of noise from the deterministic errors. And deterministic, again, was all of the things that, in theory you could actually predict what they are, even though maybe they're complicated, but, they generally have some sort of bounded type of behavior. Okay? So I believe where we basically ended up last time was kind of talking about some of the more details of the timing kind of stuff. Again, just as sort of a reminder for people, timing and jitter in particular, from whatever reason, tends to have this sort of alphabet soup associated with it of different types of jitter that people like to decompose. So again, there was this total jitter, which was TJ, which was composed of a deterministic term, which was DJ, and the random term, which was RJ. And then I think there was maybe a little bit of confusion about this last time, but basically, again, this DJ is always measured as a peak-to-peak value. So if you have a bunch of different deterministic jitter sources, you'd always add them together linearly. Whereas if you have random jitter sources, those would all be specified in RMS, and you'd add them in the RMS sense. Okay? So just as a reminder, if you have things that are sort of random noise, once I tell you what the bit error rate you'd like to get is, you can always sort of say, how many sigma of the noise of margin do I need to have? So just as a reminder, and I'll draw it in voltage, even though you should keep in mind the same thing works in time. Right? What I mean by margin is sort of from whatever your slicing threshold is, that's kind of the distance to the levels. Right? So when you specify it in margin, that's kind of the same as saying that, let's say that in this case I say that I want 7 sigma of margin for a Burr of 10 to the minus 12. That means I need 14 sigma in kind of this peak-to-peak whole height, either in the voltage domain or in the time domain. Okay, so that's just where that 14 versus 7 came from, which I think caused a little bit of confusion last time. Does this make sense to everybody? Or? Okay, so the piece that we sort of really started diving into was just kind of a reminder that timing jitter actually gets filtered also. Okay, so it's not just that you sort of directly have pure white noise or something like that. actually the timing sort of error components will get propagated through the system depending upon what type of system you actually have. Okay, so we talked a bit about sort of how people like to specify this, particularly in links that have clock and data recovery loops in them. So this was kind of this jitter tolerance mask. But where we really ended up on was kind of starting to talk about what happens in these source synchronous systems. All right, so again, just as a reminder, in the source synchronous system, what you're basically doing is taking some reference clock, usually from a crystal, feeding it to your transmitter, for example, through a PLL, but then also feeding it out through some line, going into the receiver, multiplying it up, and then using that phase to actually sample your data. Okay, so we actually sort of walked through how you derive what the transfer functions of variations on the phase here were, how they would sort of propagate to the transmitter, similarly how they would propagate to the receiver, and then finally that ended up with this sort of jitter transfer function. Right? And what I mean by that is really sort of what's the effective filtering applied on any phase noise in that reference source. Okay? And just as kind of a reminder, just to save ourselves some time, I rewrote the equations here. But basically what it really came down to was there were sort of two effects that were happening there simultaneously. So the first effect was that basically because the delay getting from the source through here, through the transmit path, is not necessarily the same as the delay as getting through the receive path. That basically means if you sort of think about a timing error kind of thing, then if I have some sort of timing error at one particular clock edge on the input source, then by the time that clock edge gets to the receiver versus the transmitter, there's actually going to be a difference in sort of which exact clock edge you're looking at where, right? So that means that, as an example, if I just happen to get unlucky, and it just happens to be that on one particular clock edge, the clock is early, and on the other one, it's late, right? Then if the early one arrives at the transmitter at the same time as the late one arrives at the receiver, it's as if you're actually amplifying the effect of that jitter, right? So in other words, that's just kind of another way of saying that if you look at this type of transfer function, which is just a 1 minus a delayed version of the same signal, you should actually expect to see some gain there. Okay, you should actually expect that there's some certain bad frequencies that turn out to be, as I said, basically bad, right? Now the only thing I should mention is that notice this is actually filtered by this additional PLL transfer function here. And the reason for that is just that if you sort of think about it, when I go through this path on the receiver over here, at some frequency, if that PLL just sort of acts like a low-pass filter on the jitter, it's just not going to track the jitter anymore at all, right? So even though you might think that that's kind of bad, that does mean that eventually you won't have this amplification effect, right? Because if the receiver is just ignoring whatever went into it, and then the transmitter is jumping around, then the worst that can happen to you is just whatever happened at the transmitter, right? Okay, so now the other effect over here was that actually, if these PLLs don't exactly match each other, that will also actually cause some ability for basically jitter to make it through and impact your link margin. Okay? So we've kind of described in words a lot of this, but what I wanted to do is actually sort of sketch what these different components of the transfer function would actually look like. So first, let's just sort of look at that delay mismatch, slightly more in detail. Okay? So just as a reminder, that's something like, just the pure delay mismatch looks something like that. Or actually, to be more precise, let me just write that as a delta t over here. Okay? So let's actually sketch that thing. So what does the magnitude of that look like versus frequency? What's sort of the shape of that curve? Okay, it does turn out to be periodic, and you actually kind of made the wavy, almost correct shape, but I'll maybe bug somebody else to give me the shape. So there's some periodicity there, but what else does it look like? And in particular, at DC, what's the transfer function?
0.
Yeah, it's 0. Why?
Well, you said S to 0. Yeah.
Well, okay. That's right. You said S to, but intuitively, right?
Intuitively, because if you don't have any, I think.
So remember, all I'm literally doing is subtracting a delayed version of a signal from the signal itself. So why is the DC, that means you get 0?
Well, you don't have any time variations on the DC.
Yeah, exactly,
so.
right? I'm basically just saying I'm taking the signal and subtracting the signal from itself, right? So in other words, the transfer function in there is 0. Okay, so now what happens is you start increasing the frequency of the signal. What's kind of the general shape?
Like
Of-
high pass.
Yeah, it looks kind of like a high pass, right? Because the faster the frequency is, the more sort of difference you pick up, right? So indeed, if we actually sketch this out, you tend to see something that looks sort of like that. And I'll just actually be slightly more careful. So all of these peaks actually line up at kind of the same point. Okay? Now again, just intuitively, what should the height of that peak magnitude be? What's like the worst thing you can possibly do? How much gain can you apply from this thing? Yeah, it's 2, right? Because the worst thing you can do is take the signal and subtract it from a 180-degree phase-shifted version of the signal, right? So indeed, this is just 6 dB here, okay? So that's just sort of the delay mismatch component. Now, I kind of point this out because, you know, some of you may have seen this before, but it turns out that particularly with sort of oscillators or just generally with references, it turns out that a lot of the noise that you get is just concentrated at low frequencies. Because that's just kind of another way of saying you don't really know exactly what the frequency is, at least relative to some other reference source, right? So this is kind of a nice behavior because it basically says that even if there's indeterminism in kind of what the exact low frequency phase is here, it doesn't matter all that much, right? As long as, obviously, that's all sort of concentrated down at the frequencies where you're still attenuating this quite a bit, right? What you would, of course, care about is that if there is a big enough delay mismatch, that this kind of, you know, this peak over here falls somewhere where you still have a lot of jitter, then that's bad news, right? Does this make sense to everybody? Or? Okay, so that's kind of, and we'll draw sort of, you know, the slightly more correct version, because obviously this is also low-pass filtered by the PLL itself. But let's also actually look at what happens with the PLL mismatch. Oops. Okay, so what I'm going to draw here is just sort of an example of what can happen there. And again, this is just going to be sort of magnitudes of various transfer functions. Okay? So just as an example, let's say that, you know, in red here, I draw the PLL on the transmitter. Okay? And let's say from whatever reason, the transmitter PLL looks something like this. Okay, so it has some certain bandwidth. Okay? Now, let's also say that over on the receive side, from whatever reason, I don't know, you know, you didn't take this class and you didn't, you know, design things right, and so, you know, your bandwidth was slightly skewed, and so you ended up with something sort of like this. Okay? So now remember that, you know, if we see over here, in terms of kind of the effect of the jitter, what you care about is actually the difference between those two transfer functions. Okay? So if I was to look at that sort of magnitude versus frequency, what does that look like given kind of these red and blue curves that I've drawn here? And I'll just label the blue just for clarity. So let's say that's the PLL on the receiver. So what's kind of the net jitter transfer function going to look like for this?
Flat go up, flat again.
Not quite. So you said flat go up and flat again. It's sort of like that. What was that?
Band pass, right?
Okay, it's band pass. So can you be more specific?
Notch.
Like where, you know, exactly, in specifically for this picture, you know, exactly, when you say band pass, you know, band pass can mean that, band pass can mean this, you know, what does it look like roughly?
You have the two poles as the two extremities,
Okay.
and then the point where both of them start falling together, that's where it becomes flat again.
Okay, you sort of got it. So you said something about the two poles causing extremities. And remember, and maybe I'll be actually slightly more clear, you know, typically we draw this thing in the log domain, right? So, you know, if I've got something down here that's even, let's say, 10 dB down from the other one, if I'm subtracting those two, if I'm subtracting something that's 10 dB down, for all intents and purposes, I'm subtracting 0, right? Roughly speaking, right? Okay, so that kind of implies that in this region in the middle here, where one of them's falling down and the other one is flat, you're just going to get some flat number, right? You're going to get just some magnitude of it going through, right? Now, down at these lower frequencies over here, right, for example, at DC, if both of them have the exact same gain, then guess what? You're going to have 0 response coming through. And particularly for phase lock loops, as we'll talk about later, the DC gain is usually extremely well defined. Because if it's not, then something's actually kind of wrong. Okay? So it turns out that these usually look something sort of like that. Okay, you know, my drawing's maybe not the best, but it's basically a bandpass filter where you get, you know, kind of a 20 dB per decade slope on one side, and the same 20, or depending upon the PLL, maybe 40 dB per decade slope on the other side. Okay? Now, just to be clear, the closer you were to get these two bandwidths to each other, the smaller this error here would get. Right? Because you can imagine as you get those things really close to each other, eventually you'd never even really get this flat region. Right? You just kind of filter it out something like this. Okay? So now again, the reason why I've sort of gone through this is because notice, in particular, as long as I match these things reasonably well, in particular, all the stuff down at low frequencies, I'm just kind of completely rejecting. Right? I'm just kind of saying, I don't really care exactly where that reference crystal started from, as long as it's only moving around fairly slowly. Right? And again, this is pretty important, particularly because, you know, these links are very common in things like memory interfaces or computer systems, where you want a pretty cheap crystal, which means its phase noise may not actually be all that great. Right? So one of the main reasons why you do these source synchronous systems is really because, notice, even though there is some possibility of amplifying the jitter, largely speaking, you tend to be actually throwing it away for a wide range of the frequency bands. Okay? Does this kind of make sense to people, or? Okay, now the other thing I should just mention is that, you know, just like with the voltage domain, where if you want to figure out the net sort of RMS jitter, you do an integration over frequency. Same thing here, right? So if I told you what was the sort of, let's say, power spectral density of that source jitter, you could pass it through these transfer functions, integrate them squared versus frequency, along with, of course, the power spectral density, and that would give you the sigma or the sigma squared of the jitter. Okay, so again, just like with voltage noise, same procedure with timing noise. Just keep that in mind because, again, for some reason, people tend to sort of get confused about how you deal with the different variables there. Okay? Does this make sense to everybody? Or?
What do you match the two gains?
Okay. Well, so it turns out that specifically in a PLL, this gain here is largely, you know, as long as the PLL is working correctly, it should basically be just the multiplication factor. Right? And again, if it's not, then probably something is kind of wrong with, you know, it's probably not working the way you wanted it to. Right? Because basically, if you sort of think about it, that gain really just means if I had X picoseconds of timing error relative to, let's say, 10 megahertz, if I take that same X picoseconds and compare it to 1 gigahertz, then from a cycle, you know, a phase standpoint, it's 100x larger. Right? So that's really all that gain is. It's just taking the same error in time and comparing it to a different frequency reference, which is exactly what, you know, that gain in the PLL is.
How about the jitter generated inside the PLL?
Sorry, can you say that again?
How about the jitter generated inside the PLL?
Okay, so that's a great question. So for the jitter generated inside of the PLL, so let's just say that I go and I add in another jitter source over here. Do I get any of this sort of matching kind of behavior? No, I don't, right? It's just a totally independent jitter source, right? So the only thing that happens there is that I just go through this delay here. Right now, that delay tends not really to do much of anything because there isn't like another path for that jitter that I'm comparing it against. So for all intents and purposes, I'm just going to be adding that jitter in an RMS way to the jitter coming from the source over here, right? The only thing that if you're, let's say, a little bit clever that you can get to maybe track is, let's say there's some, I don't know, supply noise on that buffer. If you can arrange for that supply noise to affect your reference buffer the same way, then that you might actually track, right? And so there's actually, if you look in some of the literature, they'll talk about what are the different ways to arrange this sort of source synchronous system to try and maximize the number of components that you actually track in terms of timing error. Other questions on this? Or? Okay, so this is actually kind of most of what I wanted to say about the traditional approach, except maybe to sort of highlight where it maybe doesn't actually work out so well. Okay? So remember, I said that this traditional approach was all about finding the worst case scenario, right? So as an example, and again, as you've seen in your homework now maybe, what you'd literally do is you'd find what all of the ISI components are all of the residual taps. You'd add all of them together and find the absolute worst possible thing that could happen to you and just immediately subtract that out from your voltage margin. Okay? Well, so let's say you had a really bad channel that actually had 100 taps of residual ISI in it, meaning that for some 100 symbols after your cursor, there's some residual small little error that's happening. Okay? So even if I wanted 10 to the minus 20 bit error rate, does it make sense to actually count 100 taps of residual ISI as realistically happening to me? Or does that seem unreasonable? Okay, so you shook your head no. Who thinks that's a perfectly reasonable thing to do? You know, I'm going to get all 100 of those taps hitting me all at the same time in the worst case way. Okay, who thinks that's unreasonable? Lots of lazy people in the room. Okay, so why is it unreasonable?
Because the worst case only happens like 1 out of 2 to the 100th time.
Yeah, exactly, right? That worst case is only going to happen 1 out of 2 to the, or rather I should say, 2 to the minus 100th of the time. Right? Because you'd have to add up each and every single one of those little bits to exactly stack up in the way that was bad for you. And I think I may have actually, yeah, so that's like somewhere in the range of 10 to the minus 30 or so. Okay, so, 10 orders of magnitude smaller than 10 to the minus 20, which was already a ridiculously small bit error rate to begin with, right? Yeah?
But it depends on the statistics of your data, I guess.
Okay, so...
If you are coded in such a way that it's just hits the worst ISI forever, then...
True, but fair enough. But how likely is it that your code just so happens to be the exact sequence that hits, True. Fair enough. So there are some, let's say, pathological cases that could happen. And indeed, in computer systems, this is indeed what they will tend to do. But in data communications, and actually, as you guys will see in your project, if you really counted each and every single last thing that was happening to you for, the entire period of time, believe me, you'll never find a link that you think works. But in reality, of course, they work just fine, right? So that's one sort of issue with this worst case approach. The other is that, notice, and we kind of talked about this a little bit last time, we're really treating the timing and the voltage completely separately here, right? So I just went and I calculated some jitter sort of budget, and then I calculated some voltage budget, and I said, oh, okay, well, if the voltage budget works and the jitter budget works, then I must be good. Well, so is that really true or no? No, right? Obviously, the timing actually interacts with the voltage margin you get, okay? So it turns out that, of course, there was a big group of people looking at exactly these types of problems, and that's obviously in the communications community, particularly in the sort of wireless communications community. And it turns out that the, let's say, most typical approach that people will take there is that even if you have some deterministic errors that are sort of sticking around, for example, like ISI, what they'll usually do is model those as actually being Gaussian. Okay? So they'll just say, well, okay, I've got some ISI left over. I don't really know exactly what it's doing, but let me just sort of figure out what its RMS value is and assume that it's a Gaussian distribution. Okay? So in other words, once I find what the sigma actually is, I just take that, multiply it by some factor based upon whatever burr I want to get, and then I just treat that as sort of what I actually subtract out from my link margin. Okay? So it turns out, again, this is very commonly what people will do, specifically in the sort of wireless space. And the reason I say it's sort of specifically in that space is that this turns out to work very well as long as you're shooting for relatively high bit error rates. So actually, this should be high there. So really, that should mean sort of quote-unquote low residual ISI. Okay? So again, this is a very reasonable thing to do, but turns out in our particular context, where we want, this kind of 10 to the minus 12, 10 to the minus 15 bit error rates, it actually has an issue. Okay? So to really illustrate what I mean by that, what I actually want to show you now is kind of, if I was to really look at the ISI, or if alternatively I was to really look at the timing jitter. And when I say really look at it, what I mean is if I was to actually take the distribution of that, now I was to ask, okay, what's the sort of number of millivolts of ISI that I would get versus the likelihood of that amount of ISI actually hitting me? Okay? So what you can kind of see here, and by the way, I'll tell you in 1 second how you'd really derive these distributions. What you can kind of see here is that, taking that communications approach, also kind of doesn't exactly work out. Okay, because as an example, if I look at this blue curve, which is just the Gaussian distribution that I sort of assumed that has the same sigma as my actual ISI distribution, which is this red curve, what you'll see is that the real ISI distribution, okay, matches very nicely down over here. But once you get to sort of these relatively low probabilities, obviously it has a very big deviation, right? And the big difference here is that, this distribution is actually bounded, right? Both in terms of magnitude and in terms of probability. Whereas Gaussian, that just goes out as far as you'd like to go, right? Similarly, if you sort of look at, in this case, you should kind of treat this as the jitter distribution. So this blue curve here, that would just be, again, sort of a Gaussian jitter. Just take these numbers. You can assume that they're sort of picoseconds, but it doesn't really matter. It's just sort of relative to some nominal position. Again, if you looked at sort of what you would have modeled that would give you the same sigma versus the actual distribution, you can see that even down at this sort of 10 to the minus 10 or so, there's already a pretty big error between the real distribution and your model that just assumed it to be Gaussian. Okay? So the point is here that kind of with these links, we're sort of stuck in this weird situation where this worst case doesn't really always work. But at the same time, this kind of modeling everything as just being Gaussian also doesn't really work. Okay? So it turns out that kind of the more modern approaches, what they will really do is, you can kind of in some sense say this is brute force, but they'll basically just directly figure out what the distributions are. Is there a question?
How do they find the variance in the Gaussian model?
Oh, so I'll show you how you get the real distribution in 1 second. But just as an example, let's say that I told you I had a channel that looked something like this. Okay, so there was just some number of taps over here that were small, but not 0. Okay, what I could always do is just figure out what is the variance of those residual tap values, right? So I could just treat this as a vector or whatever and find the variance of that vector, right?
Gaussian model, how do they exactly find this variance?
They literally do what I just said. So they literally just take all of these residual taps, figure out what the variance of that vector is, and then assume that that's the variance of some Gaussian distribution that's causing the ISI.
I do not understand how they do that. I understand the red curve. For the red curve, they assume that they have a...
Well, no, so the red curve is the actual ISI distribution, which again, I'll show you how you get in 1 second.
They assume a certain data pattern probability.
Yeah, so they assume that the data is equally weighted between 1 and 0.
Okay.
Right? And then they just basically actually calculate the distribution.
But
so in this blue curve here, where that model comes from is, you remember your central limit theorem stuff? The assumption is that if each one of these is sufficiently small, and each of those data bits is independent of each other, then you can kind of say, well, if I take a bunch of bimodal small distributions and add them together, it should be Gaussian at the end of the day.
So the difference is that I still don't understand. They cannot.
So again, this blue curve here is just a model. Okay, it's just literally me taking whatever the channel looks like, calculating the variance of the ISI, and then assuming that that variance gets snapped to a Gaussian model. Okay, this red curve, that's the real ISI distribution, which again, I'll show you in like one more slide, how you actually calculate it. Does that make sense? Or?
I still don't understand how they get the variance for the blue curve.
So, do you understand how to get variance in general, I guess maybe is the question?
In the red curve, I understand, but for the blue curve, even they assume all the cursors are independent distributed.
Yeah, so just assume that each data bit is completely independent from all of the other ones. Okay. So it's an IID variable compared to all of the other data bits, right? Okay, so if I have this one post cursor here, right, then I have a 50%, and you know what? Let me just do this over here, and we'll come back to it. So let's say I look at this post cursor right here, right? If I looked at the sort of distribution of that in terms of how it causes ISI, because my data is plus minus 1, right? Half of the time it's going to cause, as an example, let's say plus 15 millivolts. And the other half of the time it's going to cause minus 15 millivolts, right? Then I can go and I say, okay, well, there's this other, let's say, precursor over here. And let's say that one has a magnitude of 6 millivolts. Or actually, excuse me, 10 millivolts. Okay? Again, half of the time it's going to be minus 10. Half of the time it's going to be plus 10. right? So now I can take each of these distributions and essentially, well, I'm going to say add them all together, which really means that in the distribution you convolve them, right? And in the end, I'll get some bigger ISI distribution that includes the effect of both of these independent variables, or n of these independent variables. Okay, so for this blue curve right here, all we're doing is assuming we're not even actually going to go through that exact procedure. We're just going to assume that at the end of the day, the final distribution will be Gaussian. Okay, and so then all I care about that Gaussian is obviously what's the mean, which should be 0, and what's the sigma. Okay, so the way I find the sigma is, again, just by finding the variance of that residual ISI vector. Okay? Does this make sense to everybody? Or?
So they just plug that residual ISI into the standard deviation.
Bingo. You just do STD residual ISI, bang, that's what the number is.
So is the difference between the blue and the red dependent on how many taps you have inside?
Yeah, absolutely. Right. So in this particular example, you can actually figure out exactly how many taps it is just based on that probability. Right. So
you have like 100 or 200 taps. The difference would be smaller, or
well,
even
it
bigger?
depends. Right. So that's the trick. Is if you do 100 or 200 taps, it actually depends very much on what the values of those taps are. So we'll talk about it. Well, okay. I'll just give you the brief answer now. Basically, what tends to mess you up is, remember, the central limit theorem is averaging over a sufficiently large number of distributions, right? But if I have, for example, something that looks like that, it's going to skew the thing, right? So what happens with these link channels is you tend to have a few of these big residual ISI taps that kind of mess up the whole distribution. Okay, that's usually sort of what causes these types of errors.
But for a channel like a wireless channel, does that make more sense, or is this one?
Yeah, so for the wireless channel, this approach tends to make more sense for two reasons. One, because there tends to be a large number of small taps, because usually the equalizers are more sophisticated there. But two, and probably more importantly, notice at 10 to the minus 3, doesn't matter anyways, right? Because for that low probability, for that high probability, when I say low in Burr, you may just need to flip it occasionally, but you know what I mean, right? So at 10 to the minus 3, it basically looks Gaussian anyways, and so you don't really care, right? That's kind of the big difference. Does this make sense to everybody? Or? Okay, great. So let's say the more modern approach that people are using these days is essentially, given that there's sort of this difficulty of, both of the previous approaches don't exactly work, what you just sort of have to do is be a little bit more careful with how you treat everything. Okay, so in particular, what you'll really do is you'll just try and go and actually figure out what are the real statistics of the noise, and really more importantly, of the ISI. So here noise really tends to mean more interference rather than real thermal noise, because real thermal noise is pretty easy. Okay? The other sort of important thing is not to treat the timing noise separately, but actually to basically convert that timing noise into an equivalent voltage noise. Okay? So that's kind of just saying that, you can imagine that if I have a certain, let's say, a jitter that happens either at the transmitter or at the receiver, I can always translate that effective jitter into some effective voltage noise, right? And if I do that, then as long as, that mapping is reasonably accurate, then I can get a pretty good estimate of what the actual bit error rate should be. Okay? So there's been quite a few people that sort of worked on this space. The one I'm most familiar with, which is where I'll be presenting most of these slides from, is from Vladimir Stoyanovich. This was sort of done in his PhD thesis. So if you're interested in some more of the details, definitely go and take a look there. But I'll just kind of briefly run through just the gist of how you would do some of these things. Okay? Because we'll see it actually, this isn't just for fun. It actually has some implications on the way you build the circuits. Okay? So first of all, let's actually really look at that residual ISI. So the first point to make here is just that, generally speaking, it's actually not so easy to really just go and cancel all of the ISI. Okay? And the reason I bring that up is because you might sort of just ask yourself, well, okay, why are we spending all this time on ISI? Why don't I just build a better equalizer and completely get rid of it? Okay, well, there's a few reasons for that. The first is that generally speaking, at least if you want finite power, your equalizer will also be finite length, right? Meaning it won't be able to cover all possible taps of ISI. The second is that, even if you had an infinitely long equalizer, the coefficients you use to control that equalizer are always quantized, right? So that means there's always going to be some residual error in what you're actually correcting for, okay? the final one, which we'll talk some more about a little bit later, is that even if I had perfectly quantized equalizers, I generally can't estimate what the values should be perfectly either. Okay? So for all of those reasons, you tend to sort of end up with some residual ISI, especially if you have a sort of power-constrained design where you don't want to just spend infinite amounts of power and complexity sort of fixing all these small little problems. Okay? So because of that, we are really going to sort of go and figure out what that distribution looks like. So I guess the good news is I kind of walked through this briefly already, but just to make sure everybody got it. Procedurally, the way you go and figure out what these distributions are is you just take that sort of equalized pulse response, and by equalized I mean, you know, after you've done all of the things you're going to do to it, so DFE, linear equalizer, FIR, etc. And then you just see, okay, well, what are the magnitudes of each one of these residual taps, right? And because we're just dealing with plus minus 1 data, what I can always do is figure out what's the distribution of ISI caused by this one tap, right? And that looks very simple. It's, again, just half of the time it's positive, the other half it's negative, with that magnitude, right? So you just go, you take it for each one of these things. That gives you, let's say if you have n taps, you have n of these distributions, where the only thing that's really changing is just what's the magnitude of the voltage that you get, right? And then in your standard sort of random variable kind of stuff, you just take each of those independent distributions and convolve them together, okay? When you do that convolution, just, you know, as in this simple example, let's say I only had these 2 taps, right? With 2 taps, that kind of means with each one of them plus minus 1, there's 4 possible values, right? So it makes sense this final distribution I got has just 4 discrete values, right? Kind of plus minus 1 on each one of the individual weights. But you can imagine if I have a lot more taps, this will become a much more, you know, let's say interesting looking distribution, okay? So just to make sure that sort of makes sense, you guys will actually do a homework where you'll calculate this once, but independent of that, we'll sort of, you know, we'll look at another example here as well, okay? So what I'm showing you here is actually some, let's say, distributions for my quote-unquote real link with a real channel. So this particular one had a 5-tap transmit FIR filter, symbol spaced, not fractional. So just as an example, if you looked at the ISI distribution on the data sample, what you can see is you get something that looks kind of like this. Okay, and I believe this is actually the distribution I showed you earlier. Just here I'm doing it in the sort of in the PDF rather than in the CDF, meaning probability distribution rather than cumulative distribution. Okay? So what you can see is that, you know, now once I have enough, you know, reasonable number of taps, this kind of looks sort of Gaussian. But again, the whole trick is that these tails over here really aren't Gaussian. Okay? The other thing that's kind of interesting to notice is that if you look at this edge sample distribution over here, and by the edge sample I mean I just shipped over from the cursor by half of a data bit. Okay? If you look at that distribution, you can kind of notice sort of 2 things here. One is that it turns out to actually be sort of bimodal like this, meaning that it's not, I mean, well, actually, it does turn out to be 0 mean, but, you know, that's not where the sort of the peak of the PDFs really are, A. And B, it's also actually quite a bit wider than the distribution I have on the data sample, right? I actually have quite a bit more potential residual ISI there. So just to be clear, why is it that this edge sample looks kind of weird like this? Why is it, you know, worse than the data sample? Any thoughts?
Because it's moving.
Okay, it is indeed moving. So we can actually sketch, you know, so it turns out the, let's say the pulse response that tends to generate this kind of behavior is something that looks sort of like this. Okay, so you can see there's actually multiple points at which you cross 0. But what else is it, you know, fundamentally, why is it that with this type of system, you'd expect that you'd see actually a lot more ISI on the edge sample than you do on the data sample? So you're right, it is indeed that, you know, things are moving around at that point, but fundamentally, what's going on there?
It's closer to the next bit.
Slow by half frequency.
Yeah, you got it, right? So remember I said this is just a symbol-spaced equalizer? That means the only thing you're really controlling is what happens on the symbol samples, right? Everything in between, I can't really do anything about, right? I don't really have any control over that. So in this particular example here, because of that, these edge samples actually are a lot more corrupted, right? And again, it just happens to be that the real equalizer you build will tend to do something like this, just because, you know, when it ignores the edge samples. This turns out to be the right thing to do to try and make the data samples as clean as you can. Okay? But it's very standard that if you looked at the sort of edge ISI distributions versus the data ISI distributions, unless you do some sort of fractional thing, that edge actually looks a lot worse. Okay? And as we'll see in a second, that'll have obviously implications on how you build the clock and data recovery loop. Okay? Does this make sense to everybody? Or? Okay. So, oh, yeah.
So can you explain intuitively why is it bimodal? Just because.
Oh, it just has to do with this sort of multiple edge crossing behavior here. So it just has to do with, you know, if this was my data sample, and then I kind of shift over by half a bit right there, right? I'm not really exactly sampling 0, right? So if I take this same thing like this, and then I overlay the other one like that way, and I happen to be sampling right there, that's why I get bimodal, right? Because for the 1 bits, I'm there. For the 0 bits, I'm there. Right? If I happen to land exactly on a spot that was 0, then I wouldn't get this bimodal behavior. Does that make sense? Or?
So again, these are the residual ISIs, right?
These are the residual ISI distribution. Now, by the way, on the edge, the sort of ideal value is 0. Right? So I'm always comparing that to the ideal, like, cursor value, so to speak. Does that make sense?
This is sort of after we've implemented something and then we measure, but we've assumed the implementation, right? Or we've
Are you asking about in terms of the clock and data recovery, or are you asking about in terms of the equalizer?
in terms of the equalizer.
Yeah, so this is indeed, I've basically taken an equalizer. So as I was saying here before, since I'm looking for the residual ISI, I've already set the equalizer coefficients. So I know what the channel is, I know what the equalizer coefficients are. Now what I'm really trying to figure out is, after all that process, how much error am I going to have left? Right? Because that's what's going to sort of set my performance at the end of the day.
Ordinarily, you'd want to maybe specify in the other direction. So is it sort of an iterative approach, or?
Are you asking about in terms of the actual hardware, or are you asking
in terms
about
of the design process? Like, it seems like this is something you'd want to know up front, but instead it's something.
Okay, that's right.
afterwards.
So for certain channels, and I guess, well, maybe since you didn't raise your hand on starting the homework, you haven't seen this yet, but you know, you'll see this. For certain channels, you can actually calculate what this should look like, right? If the channel was simple enough, I can kind of just derive very quickly what should the ISI distribution look like, right, as a function of the number of taps and things like that. But remember, you know, okay, I guess I don't have the pictures here. But remember, a lot of those channels look, you know, something like that, right? Kind of tough to, I mean, I can do it maybe, but, you know, I think MATLAB is much better suited for just, you know, running it and figuring out what's really going to happen. So you're right, there's obviously some iterations there of, okay, I try a 5-tap equalizer, oh, that doesn't look so good, I add a DFE, etc. But I'm not sure that there's, you know, at least for real channels with lots of weird stuff happening, I'm not sure there's really a better way of doing it. If you come up with one, let me know. Other questions on this? Or? Okay, so the other sort of big piece of fixing this model is not only do you really want to know what the ISI distributions are, but you really want to take into account this effect of the fact that changing the timing will also have an impact on the real voltage margin that you get. Okay? So just to make that clear, there's sort of, you know, one very simple picture we can draw, right? So let's say that this green line here was where I ideally wanted to sample, and I get obviously the most voltage margin at that point. Well, if I shift my voltage sample over, what's going to happen is that, first of all, I'm going to get smaller voltage margin sort of relative to my threshold. But second, if you actually look at the details of the distribution there, it's actually different, right? The residual ISI that's, you know, popping onto the data in that red spot right there, and let me do this with a black highlighter so you can see, right? This thing is obviously taller than this one is, right? So you actually have to sort of know not only kind of what the new voltage margin is, but really what's the new details of this ISI distribution depending upon where you're actually doing the sampling, okay? So that's what we're going to sort of quickly walk through now. It turns out it's not quite as bad as it may look, although, you know, there are some slightly annoying equations in there. But basically what this will really turn out to happen is that exactly sort of the effect of timing on your voltage margin turns out to really depend upon, obviously, how big the jitter is in the first place, what's kind of the input sequence you're talking about, but finally, and really most importantly, what's the channel characteristics? Okay, because as we'll see in 1 second, the jitter actually gets impacted by your channel characteristics, okay, in a kind of indirect way. So let's just sort of start thinking about how we can analyze something like this, okay? So let's say the simplest way that I know of is you can imagine that, let's say I had some ideal pulse that I wanted to transmit. And by the way, I'm going to start on the transmitter because it's going to turn out the transmitter is actually more important than the receiver from a jitter standpoint, okay? So let's say I have this ideal pulse that I've drawn in green over here. And let's say that I have some jitter that, for example, shifts this first edge to the right and also shifts this next edge to the right, okay? Well, so in other words, my real transmit waveform is now this red thing over here. So purely so that I can come up with an analysis that would tell me what the impact of the jitter is, independently of my signal path, you can imagine that I can kind of decompose this thing into something that always has the ideal transmitted pulse, plus these two sort of error pulses that are just compensating for the effect of that whole thing being shifted, right? So as an example, if I shifted that green pulse to the right, and that kind of means that initially I'm subtracting some voltage off. And then if I again shifted this red thing over to the right over here on the other edge, then I'm kind of adding an extra voltage over here, okay? So in terms of the analysis, what I'm going to do is I'm just going to treat this quote-unquote, jitter as being the noise. And this is just going to be sort of my ideal signal transfer functions, okay? Does this make sense to people? Or okay, so now, just maybe to prefetch slightly, does this look like easy to deal with to you, or does this still look pretty annoying? And again, by pretty annoying, I mean going and actually doing some, even hand calculations with something like this. Okay, so I see some people shaking their head. Why is this still annoying? What do you have to do to kind of work with this? Or rather, what's changing as the magnitude of the jitter changes? Yeah, so you made the right motion. You basically said, okay, if I have more jitter, that's kind of changing the width of this pulse, right? I don't know about you guys, but I don't like doing math with variable width random pulses, right? Passing that through some linear transfer function, okay, I'm sure I can do it, but it's a pain in the ass, okay? So turns out that what you instead will do is just make a very simple approximation that turns out to work nicely in just about all sort of scenarios that we really care about, okay? So the approximation we'll make is the following. We'll say, let's take these sort of variable width pulses, which remember, the width of those pulses is basically set by the magnitude of the jitter. And then instead of dealing with these pulse things, why don't I just say, well, you know what? This thing looks a lot like a delta function, where the area of that delta function, which really means the quote-unquote magnitude, is just the same as the area of that original pulse, okay? Now, the reason this works is because remember, at the end of the day, I'm going to be taking these sort of narrow pulse things and passing them through a low-pass channel anyways, right? So if I'm taking a narrow pulse and passing it through a channel, why the hell do I care if it's a narrow pulse versus a delta as long as the areas are about the same, right? Because as long as all of that stuff is short compared to your channel bandwidth, it all is going to give you about the same answer anyways, right? So that's really kind of the key in terms of getting some, let's say, simple analytical results out of this thing, which is just to say, let's just pretend that the jitter is actually these impulse delta things. And so now I can just say that the sort of height of that delta or the area of that delta, that's what's set by the magnitude of the jitter and not sort of the width of that pulse. Okay? Okay, so once you do something like that, you can basically come up with a model that kind of looks like this. Okay, so I'm not really going to walk through the equations, but I'll just sort of maybe point out a couple of the key points here. So what we're basically doing now is kind of everything that's up on the top over here, that's kind of your standard, signaling path. Okay, right? So you imagine you have some data, which here I've just called AK. We're going to pass it through some equalizer, which in this case I've assumed is on the transmitter side, right? So that's going to be some, let's say, W matrix or equalizer here. I'm then going to send that through my channel, which in this case I've just modeled as being some pulse response with lowercase p. Then it's going to go into my receiver, which I'm just going to be modeling as a slicer, right? Okay, so, but now what I'm going to do is, because remember I want to include the effect of the jitter, I'm going to say, well, actually there's this extra path over here, right? Where this path is basically going to be taking the jitter from, for example, my PLL or my clock system or whatever it is. I'm going to multiply it by the data because notice sort of the height of this pulse is also related to the height of the data. So I do have to do that multiplication. But once I do that, I can kind of say, well, if there's some impulse coming out of here, I can pass that impulse also through my channel, right? The only difference is that now instead of passing a pulse through the channel and measuring the pulse response, I'm going to pass this impulse through the channel. And then again, I'm going to measure what's the effect of that impulse, not at exactly the same delay, but actually at a delay plus half a bit time, right? Because remember, what I want to know is what's the impact of this jitter on your data sample, and not necessarily on the edge sample. Okay, so that's where this t over 2 is coming from here. Okay, does this kind of make sense to people, or? Okay, so turns out, this pile of, okay, it's not such a bad equation, but this pile of equations over here is really just stating what we just said. It's just really walking through this model and then trying to figure out what is the transmitter jitter actually, or really what's the overall jitter actually going to do to you. Okay? So there's just maybe a kind of couple of things that I want to point out here. So the first is that basically this term right here, this is kind of telling you what's the effect of the jitter due to kind of the current bit. Okay? In other words, this is sort of telling you, if the jitter that was on my bit that I just transmitted, how is that going to impact my voltage margin? Okay, now, so you should notice here that for this, I really do have to look at the difference between what was the basically receiver's phase and what was the transmitter's phase or the transmitter's jitter for that particular symbol, right? You can imagine that that effect is then also going to be sort of relative to what happened on the jitter for the next data period, right? Because you can imagine if that clock edge either moved in or moved out, then that'll kind of impact the width of the pulse that I sent in the first place, right? And then again, I'm going to look at the difference between what happened on the receiver versus what happened on the transmitter. But there's one sort of key thing which you should notice here, which I'm going to sort of point out in more detail in 1 second. You should notice that for the receiver side, I'm going to use the same jitter value for both the effect of the current bit as well as the effect of the next bit. Okay? Whereas for the transmitter, it's actually previous bit versus next bit. Okay? So to kind of give you an intuitive feeling of why that's sort of important, you should keep in mind sort of one thing. Okay? So at the transmitter, if I get some jitter, that's really literally going to affect the shape of my waveform, right? I'm literally, if I got, something that was late and something that was early the next cycle, I'm literally going to get a short pulse, right? On the receiver, if I have jitter, it's as if I just took the entire transmit sequence and shifted it over by that amount, right? But I'm not actually changing the width of that pulse, okay? So that's actually why you end up with sort of this initially weird-looking situation here. Okay, so just to sort of say it another way, on the transmit side, again, what you really don't want to have happen is that you end up sending a narrow bit. Because remember, you're going through a low-pass channel anyways, so if you send something that's even narrower, you're going to get even less signal at the end of the day, right? So this is kind of saying that on the transmitter, really that high-frequency jitter is bad, okay? Because to say it sort of, the statistics way, kind of this k minus j and this k plus 1 minus j, they end up being uncorrelated, and so they add statistically. Okay? In contrast, if you sort of think about low-frequency jitter, where again, literally all I'm doing is just taking the entire transmit sequence and shifting it, not that big of a deal, right? As long as my receiver can kind of track that, or even if it doesn't track it, then now I'm just literally shifting the whole waveform over. Right? And as long as my received sort of shape was kind of flat in that region, may not even have that big of an effect. Right? So the trick here is that, as we were mentioning on the receiver, it's really always equivalent to just shifting that whole waveform over, right? And that's kind of what this picture here is showing you. It's just saying that, if instead of sampling at this perfect green point, I sampled at that red point, that's kind of equivalent to just saying, why don't I just take the transmit sequence and shift it over by that amount, right? So that says that, unlike on the transmitter, the receiver always, quote unquote, looks like low frequency jitter, meaning it's always just shifting the whole sequence around. Okay? So if you really sort of work out the implications of that, what it basically says is that if you take the same amount of jitter with the same frequency spectrum and you apply it on the transmitter versus you apply it to the receiver, the effect of the transmitter will actually be much larger. Okay? And well, maybe not much, but depends on the channel, right? So, and that's kind of what this plot here is showing you. It's basically saying if I took just a white jitter source and I just applied it onto the transmitter and I looked at sort of the equivalent voltage noise that caused versus the voltage noise it would cause on the receiver, you can see on the transmitter it's actually, for the same exact jitter magnitude, causing you almost an extra 10 dB of noise down at that lower frequency, right? So you can kind of see uniformly it's always causing you more voltage noise than what the receiver actually was. Okay? So just maybe to put it in kind of a communications term, this is kind of saying that the transmitter jitter is actually enhanced by the channel. Right? So it's kind of like the noise enhancement of the equalizer. It's just that it's sort of in the jitter domain rather than really some signal processing thing that we're doing to it. Okay? Does this kind of make sense to people? Or so if you have a question, you should feel free, because when I first looked at this, I was confused as hell. So no questions. Okay, so maybe that means I need to give you a homework or something like that on this. Okay, well, so just as kind of a final note there, of course, here I just used white jitter sources. Of course, in reality, the jitter also has some filtering, as we said before. So whatever that total bandwidth of jitter is would set the actual magnitude of the sort of error that you would get. Okay? So far we've been sort of just abstracting, assuming that I kind of knew what those random jitter sources were. But remember, there is actually always this clock and data recovery loop, or there's some sort of way of figuring out what the timing should really be. Okay, so in particular, if you look at the CDR, then when I really start talking about this jitter, what I'm basically saying is I don't need to know only the jitter really coming from that PLL, which maybe I'd model as just adding in at that point right there. But what I really actually need to do is figure out what's the jitter on this real sort of sampling data clock, right? It turns out that's actually a little bit more fun than you might think it is, because remember, the way I build this thing is I actually have some sort of feedback loop, right? Where I'm actually looking for transitions and then adjusting my clock position based on those transitions. Okay? So anybody have any thoughts on how you can kind of deal with this? And by the way, remember, at the end of the day, what you really want to know is what is the distribution of that ISI, or excuse me, of the jitter, so that you can actually then go and calculate really what's the distribution of the voltage noise that you'd create. So how might you deal with something like this, where you've got this feedback loop that's got a integration filter in it and things like that? How are you going to go and sort of figure out what this thing is kind of doing to us in terms of the steady state behavior? No thoughts? Well, okay, I guess I can bug the people that I know have written the code for that before, but that's not so much fun. Well, what's like the, anytime you get something complicated, what's usually the first thing you'd like to do?
Simple model.
Okay, well, yes, you'd like to come up with a simple model. That's absolutely correct. What's usually the simplest model you can come up with?
Linear model.
Okay, there we go. Usually you like to just come up with a linear model, right? You just say, well, okay, this whole thing is gross and nonlinear. Let me just figure out some sort of linearized model that tells me the answer. Okay, so it turns out a lot of the initial work was indeed doing exactly just that. So they basically say, well, this whole thing just kind of looks a little bit like a delay lock loop, right? Because I basically get some timing error, and then I just take that timing error and sort of pass it through some filter, and then feed it back, right? And indeed, you can actually come up with a model like that works reasonably well. Okay? Turns out you can actually do sort of slightly better than that without even introducing too much, let's say, nastiness in terms of computing things. Okay? So the particular model that I'll just kind of quickly walk through here is actually, rather than sort of treating it as just a linearized system, to actually just say, well, okay, this whole thing is just a big state machine. Okay? And you can kind of think of it as the state is just where your current phase position actually is. Right? So if I know where my current phase position is, and I kind of know the shape of the waveforms, what I can always do is go and figure out what's the likelihood of me moving from that current phase position to one of the other phase positions, right? Or really to any of the other phase positions, right? Now, in particular, usually the way you do this is you just have, remember we just sort of build these bang-bang kind of things, where all we really know is do you go up or do you go down? Okay, so just as an example, you can say that, well, okay, if I knew again what the shape of the waveform was, then at a given phase offset, let's just say I arbitrarily pick 100 here, I could figure out, okay, well, given the shape of the waveform and sort of where my cursor is really sitting, I can figure out that, statistically speaking, I have, let's say, a 70% chance of moving up, right? But I also actually have a, whatever this is, maybe 10% chance of moving down, okay? So what I can actually then go and do is just compute for each of these phase positions, what's the chance of me moving to the next, either the +1 phase position or the -1 phase position, right? Once I basically have that, then actually life is pretty easy. And I should only mention one thing just to sort of make sure it's clear. Remember, if you don't get a transition, then you shouldn't actually make any updates. Meaning if the data didn't actually change value, then you don't have any timing update. So you can include that effect as well, which just kind of visually on these curves here, it just means that if there's a certain probability that you didn't actually have a data transition, meaning that you don't actually have any knowledge as to what the timing is, then obviously anytime you don't have a transition, you can't make an up or down decision. Right? So that just gives you sort of another curve here and scales these up and down curves appropriately. Okay? But basically, once you sort of have these things, turns out you can really then figure out what's the sort of steady state chance of you being in any given phase point. Okay? Now I should just mention sort of one thing here. Notice that, as I move from kind of roughly this point over here, as I move in the up direction, meaning I have more, I'm increasing the phase state, notice that the probability of going down increases. That's good news because it means that, you will be pushed back towards the right spot, right? Because as an example, if the probability of going up increased as you were going up, this whole thing would be unstable, right? Like you just get stuck on one side or the other, okay? So again, kind of the point here is that indeed you're likely to kind of move in the right direction. But if we really want to know what the impact of the jitter is, we actually have to go and look at this distribution and really figure out in steady state, where are you going to be sitting on these different phases, okay? Okay, so basically the way you do that is actually with a relatively simple sort of model. What you basically just say is, okay, at any one given phase position, I know what the probability of moving up or moving down is, right? So what you can kind of do is think of that as kind of like a big matrix that tells you, if I give you the current state, then I can tell you what's the probability of me ending up in the new state, right? Well, once I know that, I can then take that new state and again pass it through that same probability matrix to figure out, okay, what's the new sort of state distribution that I'm going to get into, okay? So in other words, you just keep applying that probability of transition over and over and over again. And eventually what should happen is you get to some steady state distribution, right? For those of you guys who like statistics stuff, this is just another way of saying that you use a Markov chain or a Markov model. It's the same thing, okay? So once you do that, what you will end up with is something that looks sort of like this. Okay, it'll basically say, okay, this is really the probability distribution function of your different phases. And remember, those phases also just correspond with what's the timing offset that you're sitting at. Okay? So in other words, this is now really the quote-unquote jitter distribution. Right? Because you know that, let's say, nominally you'd like to be here. But because there's a 10 to the minus 5 probability that you'll be off by, in this case, about 20 phase codes or so, well, that's, if I was to ask you the question of what's the probability of having a certain amount of jitter, this is the distribution that you would use to figure it out.
Question.
Okay?
Question.
Yeah.
Why is the on previous slide? Why is the p no value transition always a half?
Oh, so this is just assuming that the data sequence is totally uncorrelated. So if, for example, if I was a 1, the chance of me staying the same the next bit is a half. And if I was a 0, the chance of me staying the same the next bit is also a half.
I see.
Right, so that's why.
It's because of the data pattern you transmit.
Right, it's just assuming that I'm transmitting completely random data in terms of its, in terms of its sequences and the correlations between the bits. Okay? Obviously, if you had some coded pattern or something like that, this wouldn't necessarily be exactly true. But there's other issues that you'd run into if you're not careful about it.
So the transition region is basically defined by 1, the thermal noise, and then 2, the residual I side?
That's right. That's right. So it's actually defined by the distribution, or rather I should say by the distribution of the voltage signal at the edge sampling location. Right, so this shape here is not just something I arbitrarily came up with. That's where it would come from. And indeed, you have to include with that the thermal noise and all of the other jitter and etc. effects. Or I should say random, truly random jitter. Does this make sense to everybody? Or?
What are the units of these phase counts?
Oh, okay. So that depends on how you've actually built your clock and data recovery sort of state machine. I think in this particular example, it turns out to be 1 picosecond. But that's kind of arbitrary, right? Because you can imagine that really depends upon what's the resolution of kind of your integration register that's sitting there, as well as even just what's the resolution of the sort of phase interpolator or phase rotation thing that you're using to create that output phase, essentially. Does that make sense? Or? Yeah, so you can actually, there is one limitation to this particular thing, which is, notice, I've only done this with kind of a first order loop. If I started including things like loop delay and multiple integrations, life gets fun, to put it mildly. Because then you have these, you can think about this as these big two-dimensional Markov chains and things like that. Most people I know don't really deal with that. They sort of assume that if they have higher order integrations, then basically they kind of ignore the effect of those other things because they assume that that's just sort of find an average frequency. And then they largely use this to kind of predict roughly what the jitter distribution will look like. We'll talk some more about that a little bit down the road when we get into the details of kind of CDR design. Does that make sense, though? Or? Okay, great. So why did I sort of bother dragging you through all this math and stuff like that? Well, the end point of the day is that indeed what we'd like to do is take a given link design, let's say with a 5-tap transmit preemphasis and a DFE or whatever it is, and really figure out, is this thing going to work? Is this going to get me the bit error rate that I actually want? Okay? So the way you will do that is you'll basically, once you've gone and you've calculated all these distributions, what you can kind of conceptually think about is you can just go and put these distributions on kind of like, this won't exactly be an eye diagram just yet, but it kind of sort of looks like an eye diagram, right? You can kind of say, okay, well, nominally I should always be at kind of one of those 2 points, right? Like if I had a perfect system, and let me just draw it in black so you can see. If I had a perfect system, then what you'd always want is you'd always get exactly just, I would sample exactly right at that point with a peak magnitude, right? Well, okay, but as we said already, in this kind of slice direction over here, which is just changing the voltage, I've got my residual ISI distribution, right? So kind of the color map that's being used here is just being set by that residual ISI. Similarly, in time, right, what's actually going to happen is that because of that CDR distribution, I could land in a different point. I could land at a different sampling position, right? So the only, let's say, additional funniness is that I also, of course, have a different ISI distribution in voltage at that time, right? So this kind of funny-looking plot here is just trying to sort of vertically show you what each of the ISI distributions are, and then horizontally weight all of those ISI distributions by the timing distribution. Okay? Does this kind of make sense to people, or? Yeah.
Saying that they're more sensitive to timing variations, or timing variations lead to a larger variation in, I guess you're putting utility or the output.
Okay, so here's the subtlety. This is not yet the bit error rate. This is only showing you what is the ISI distribution and what is the timing distribution somewhat independently. So to actually get to Burr, what you sort of have to do is convolve these things together, right? Because for example, even if I'm nominally supposed to be here, I have to sum up all of the weights of the stuff around me in time, as well as the voltage ISIs I could be seeing on those times around me. Right? So in other words, you can kind of think of this conceptually as if nominally I was at this center point, then sort of my chance of, for example, being right there is going to be this probability times that probability, plus the probability in time of me being here times, for example, the weighted average of that ISI distribution, and so on and so forth. Okay? So at the end of the day, what you actually want is this so-called Burr contour. Okay? So the only difference between this point and this point is I just did all those convolutions to figure out at any one given point what was really the probability of me being there. Does that make sense? Or? So in other words, here I'm literally just trying to show you what the distributions look like, but I haven't convolved the time and the voltage together yet. Okay, the only way I've done it is just by sort of scaling the colors based upon the time. But I haven't actually told you yet, if I really was at this point and I included all of the statistical distribution, what the Burr would really be. That's kind of the difference. Okay? Yeah. Okay, so basically that color code is in the vertical direction, it's the residual ISI distribution, but it's just weighted by the timing distribution in the horizontal direction. So in other words, you can kind of see, timing-wise, it's highly unlikely for me to be out over here. Right? And so that's why sort of the color is getting, in this case, more towards the black or towards the cool as I move out on those timing directions. This one I actually converted the sort of phase codes into real picoseconds. Oh, so I believe this is log 10 of the probability. Something like that. Although really, don't take it too literally because this is just sort of conceptual to give you an idea of what it looks like. The one that I think is more useful is actually once you've done that convolution, now I can really show you these so-called Burr contours. Right? So I can really say, okay, if, for example, I told you that my slicing threshold is at 0, and I asked you if I nominally set my sampling point to, just as an example, let's say 100 picoseconds here, right? Then you can say that, okay, the voltage margin I have at that nominal sampling point is this distance, right? And that voltage margin, by the way, would be specified at a given bit error rate, right? So this margin here would be if I wanted, let's say, 10 to the minus 30, then that would be the voltage margin I have. If I want, for example, let's say, I don't know, 10 to the whatever that is, 10 to the minus 20 or something like that, then obviously you'd specify it down to that new horizontal line there. Okay? Does that kind of make sense? Or? Now, what you can notice here is that even though at this, if I was at this nominal point here, then that's kind of the voltage margin that I would have. Right? You can see that this is kind of, it's not exactly, but it's kind of showing you a little bit what the eye diagram looks like. Right? Because it's kind of saying that, look, all that has to happen is if you move over by about 20 picoseconds or so, then notice at kind of, 10 to the minus, let's say, 20 or so, you've got a much smaller margin there. Right? In fact, you might not even actually be able to receive that at that bit error rate. Okay? So the number here is kind of arbitrary. So you should sort of treat this as like relative to the symbol delay. So in this particular case, the symbol delay, or the symbol period, I should say, was 160 picoseconds. Okay, so this particular plot, I think, was just sort of drawn to show you if you were at exactly sort of the center of the quote-unquote symbol, what would this thing look like? And in this particular case, by the way, because this thing, as I said, this thing only has a 5-tap transmitter. It turns out it has some residual ISI on the edge. And so when you figure out the CDR lock position, it's not really at the best point. That's right. So in this particular case, you would have actually gotten much better performance if you sampled it at 100 picoseconds rather than at 80 picoseconds. Yeah, basically, yes. That's right. That's right. Right. So, and by the way, indeed, this is quite realistic because remember, the CDR that we're using is not, magically optimizing the voltage margin. It's just doing this sort of looking for transitions, right? And so if your edges are dirty, then indeed you'll lock to the wrong position. Okay. And so this is kind of showing you the impact of that, right? Because as we said, if I could sample at 100 picoseconds, I'd have that much margin. But because maybe I'm sampling at 80 picoseconds, I only have that much margin. Okay. just as an example, obviously. Does this make sense to people, or? Okay, now, the good news is that if you go through all this so-called hard labor, then it actually does give you a pretty reasonable way of estimating your performance. Okay, so just to kind of convince you of that, this is just a plot that was done. Basically, these blue curves were sort of taken from a tool that was doing all of these, Burr contours and ISI distribution calculations and things like that. And these red points were measured from the real hardware that tool was actually modeling. Okay, and what you can see is that, okay, now fine, down over here it's not exactly working, but probably at that point you don't really care anyways. But the rest of this point is actually matching pretty reasonably well. Okay? Now, I should be a little bit, let's say honest here. This one actually matches really, really nicely, largely because this particular link was totally dominated by residual ISI. And that one is actually probably the easiest one to calculate accurately. So, if jitter and things like that were a bigger deal, then you may have seen more deviations here. But nonetheless, it actually works out pretty well. It certainly gives you enough insight to kind of get going in the right design direction. Yeah. Yeah, so the way this was actually measured was basically, you would take the comparator, and then let me draw that more nicely. You'd basically take the comparator, and then essentially offset its reference voltage. Right? So for example, if you knew that 0, well actually you can see in this case, what is supposedly 0 is not necessarily, actually in this case it is actually, let's say, the best. But all I have to do is if I just start offsetting that threshold, then what I can kind of do is trace out what the bit error rate is as a function of that threshold. Right? So this is kind of like a waterfall curve, just in voltage rather than in time. Does that make sense? Or? Yeah. Well, no. So if I take the ISI distributions, and I'm not just at one particular point, but across the entire eye, I then use those to calculate the CDR distribution and the jitter, sigmas, and things like that. And then I convolve all of those together. I'm including both the timing and the voltage noise. So this curve is just basically taking one particular point here and essentially sort of slicing it in one direction. Okay, so it's kind of saying that if I was to offset, by this amount, meaning I was to take away that much margin, what's the bit error rate I would expect to get? No, so that's what I'm saying is, remember, the difference, right, on this slide right here, this is really the Burr contour, right? If I was on here, then it would just be the ISI distribution. But remember, what I've done is that for each of those sampling positions, I've actually figured out how much additional junk am I picking up from all of the regions around me that statistically I will occasionally jump to. Does that make sense? Or? Yeah, question, Linkai. Which noise? The thermal noise, you mean? Oh, okay. Well, so I guess it depends on the exact circuit you've built. The good news is, though, that most of the real thermal noise doesn't really care where the sampling position was.
That has, that has a shape, right? It's not white. Yeah, when you use the model, it's not exactly.
Yeah, fair. That's right. Although, for most of, let's say, the practical things that I've seen, needing to worry about the exact sort of, let's say, quote-unquote shape of that noise probably wasn't so important, in the sense that, largely speaking, what you kind of cared about was, kind of what was the, like, remember, I'm not asking the question of, if I made an error this bit, what's the probability I make an error the next bit around? I'm just looking for, on average, what's my bit error rate? And from that standpoint, mostly what I just care about is what's the sigma of the noise, right? And that doesn't really vary all that much depending upon exactly where I've sampled the thing, right? So what you could be saying is that, well, actually, the jitter dynamics interact with the voltage noise dynamics. That's true. Both of those are small enough already that usually that doesn't matter. But that is true. Chintan, do you have a question?
So, in theory, if you wanted to add on normalize on top of the curve on the last slide.
So by the way, this already includes thermal noise. So this is like the, because again, this is actually measured from real hardware. And with real hardware, it's kind of hard to take the thermal noise out. But so this actually includes the thermal noise.
Yeah, I was just thinking if there was more thermal noise, then you would have, if you took multiple measurements, then you would have got multiple points smeared around the Around the estimator?
Oh, well, no, I mean, even here with the measurement, you can kind of see, right, like there's these deviations here. Because this is really just the difference between sort of, even the bit error rate itself is a statistical quantity, right? So just because I measure it once doesn't mean I'm going to get the exact same error the next time around I measure it. So to really get these points here, you actually have to do sort of, let's say, a significant enough number of trials that you actually believe this bit error rate number that you've measured here.
Then if it does include the thermal noise, then why did you say that this was dominated? I mean, why did it make a difference?
Oh, because in this particular channel, because of the way that system was built, it happened to be dominated by residual ISI and not by thermal noise. In other words, the equalizer wasn't sophisticated enough to really get rid of all of the ISI, and so that was kind of what was dominating the behavior.
Even if it was not, you would still have got the matching to happen.
I can't claim that since I haven't done the measurement, but as far as I know, and as far as from the people I've talked to and stuff like that, yes, I think that would be a very reasonable thing to get. Okay, other questions on this, or? All right, so I promise we will dive back into circuits next time, but as I said, this is fairly useful and important because it'll tell you sort of what's the circuit you actually have to build. So I'll see you guys on Thursday.